These are the 6 basic shapes in this quantum module system, and they can all be built from the basic tetra and octa modules. Now I'd like to show how these shapes are related to each other and some of the basic geometric characteristics that they share. These shapes all coexist on a virtual plane that are based on 13 unique intersecting planes. 4 of the planes are based on the tetrahedron as well as the octahedron, and they are illustrated by a black and white pattern. 3 of the other planes are based on the 3 planes of a cube and are illustrated by the blue faces you'll see. And the other 6 planes are related to the 3 versions of the rhombic dodecahedron, of which the orange, red, yellow, light green, and dark green colors represent the occurrence of the rhombic dodecahedron planes. Now I'd like to describe a little bit about the positional relationship between these shapes and the various planes that are contained in this system. I'm going to start by defining a reference grid, the Cartesian sort of system, x, y, and z, and this lines up perfectly with the geometry of a cube, and the planes line up with the x, y, z plane. But let me first start with the octahedron, which is centered at the origin of the Cartesian system, and the planes you can see start to take shape of the octahedral planes, and they've been rotated by 45 degrees and rise up at a 54-degree angle roughly. Now this could seem a little clearer where the tetrahedrons now could connect to any one of these faces, and here you can see a little bit more clearly now the creation of the octahedral planes. If we now build in a cube, which is centered around the tetrahedrons, you can see now how this blue plane is taking shape in its relative position with the octahedral planes. Now if we create the orange version of the rhombic dodecahedron, which is also centered at the origin and around the octahedron, you can see now beginning of the RD plane showing up in orange, at least one version of it, and it's at a 45-degree angle in many cases with the cubic planes. If I proceed now and try to add in another version of the rhombic dodecahedron, this is a two-tone green version. Now you can see the extension of the orange color with the two-tone green to continue that rhombic dodecahedron plane. And now if I can add in the third version of the rhombic dodecahedron, it sits here like this, and now you can see all 3 occurrences of the 5 colors of the rhombic dodecahedron all in one plane. And the center of this rhombic dodecahedron, from the yellow and red, is actually centered at the vertices of the tetrahedron and octahedron. Now I'll be using some diagrams and a CAD tool to help illustrate how space is partitioned by these 13 planes in a quantum module system. Figure 8 shows 3 planes related to the cube, which will be used for the first partitioning. We'll start with 3 pairs of the cubic planes, seen here, to partition up space, which will create 8 cubes. We'll then take one of these cubes and further divide it up with the 4 planes of the tetrahedron and octahedron, seen here in figure 9. These planes are rotated by 45 degrees to line up with the diagonal of the face of the cube. Now we use the 6 planes of the rhombic dodecahedron to further partition the space, and as a result the space has been partitioned to 48 modules, 28 tetramodules and 24 octamodules, and all of the modules reside on the virtual grid created by these 13 planes. And the other way to view these 6 planes that you just saw in figure 10, you'll notice that this cube has these X's on each of its 6 faces, and that represents an RD plane cutting through the cube. And if I can slice it open, you can see now the 5 unique colors of the rhombic dodecahedron. And you see bits of the orange rhombic dodecahedron, a section of the red-yellow, and you also see the two-tone green RD. And if this gets extended out, you'd see the full pattern. So in essence, in summary, you've just seen the 13 planes in this system. And another way of looking at the system is that those 13 planes have taken plain old 3D space and carved it up with the 3 planes of the cube to get one division. It's then sliced up by the 4 planes of the octahedron or tetrahedron, and then 6 more times with the rhombic dodecahedron to make these individual parts that make up the system. Now let's take a look at the arrangement of the rhombic dodecahedron planes and the planes of the cube. I'll do this by rearranging these to create this kind of a brick shape. But now you can see clearly the cubic planes on both sides here, and now at a right angle to the cubic planes are now the portions of the rhombic dodecahedron plane, and you can see the orange section here, the red-yellow portion here, and the two-tone green on the sides. Let me illustrate the relationship between some RD planes and cubic planes. I just need to rearrange some parts to create a new structure. There's a tetrahedral plane, or octahedral plane. Let me build up the other side with some other submodules you've seen earlier. There's another occurrence of a tetrahedral plane. Now I'm going to take another piece similar. Need to connect this to a larger structure that's a hexagonal prism. You can see on the sides the occurrence of the orange rhombic dodecahedron, as well as the two-tone green and a portion of the red-yellow rhombic dodecahedron. And it's at right angles, the RD planes are at right angles to the tetrahedral planes.